In this video we'll discuss Green's theorem, which relates a line integral around a simple closed curve to a double integral over the region that is enclosed by that curve. So to state the theorem, we have to imagine having a simple closed curve in the plane. So let's call this curve C, and we have to agree on what we mean by a positive orientation. So our convention will be that the curve is positively oriented if the point traversing the curve always has the interior of the curve on its left-hand side. So this orientation, this way of going around the curve in this drawing, would be the positive orientation. Okay, and if we would go around the curve the other direction, that would be our negative. That would be the negative orientation. So imagine having such a curve. More precisely, let's see be a positively oriented but also piecewise smooth. So it consists of pieces that are smooth curves. Simple should be a simple curve, meaning that it does not cross itself, and it should be closed. So it's a simple closed curve in the plane. And let us use D to denote the region enclosed by this curve. So D would be the interior of this curve. So then, if we have two functions, P and Q, each depending on x and y, so we have two functions of two variables, such that they have continuous partial derivatives over this region D, so they are continuously differentiable over D, then Green's theorem tells us that the following relation will hold true if we take the line integral of P with respect to x plus Q with respect to y along the simple closed curve C, then that is equal to the double integral of dq over dx minus dp over dy over this region D. So that's our statement. It relates a line integral to a double integral. So this is the partial derivative of q with respect to x minus the partial derivative of p with respect to y. So let's see an example. Let me ask the following question. Evaluate the following line integral. 3y minus e to the sine of x dx plus 7x plus square root of y to the 4 plus 1 dy. So use Green's theorem, this statement, to evaluate this line integral along the circle that is given by the equation x squared plus y squared equals 9. Pause the video and input your answer below. Okay, I hope you paused it and realize that if we look at this function and call it p of xy and call this other function of x and y q of xy, then we can apply Green's theorem to evaluate this line integral by evaluating the double integral over the region that is the interior of that circle of radius 3. So that is the disk centered at the origin and which has radius 3. And the function that we are integrating is the derivative of q with respect to x. So differentiating this function with respect to x will give us 7 minus the partial derivative of p with respect to y. So differentiating this function with respect to y will give us the number 3. And this we want to integrate over that disk of radius 3. So that's just the number 4 integrated over a disk of radius 3. So that is giving us 4 times the area of that disk. So that's 4 times the area of a disk of radius 3. So remember that the area of a disk of radius r is pi r squared. So it's pi times 3 squared. So that's 9 times 4, 36 pi is what we get for this line integral, for the value of this line integral. So that's one example for where we can use Green's theorem to evaluate a line integral that would otherwise be almost impossible to evaluate. Just try and evaluate this line integral in the usual way and you will quickly see how difficult that is. So let me just point out that if this combination of partial derivatives is happens to be equal to 1, then we are integrating the constant function 1 over this region D. So then we get the area of that region. So it can be used, Green's theorem can be used to find areas of regions in the plane. So let me just say that if, for example, we have Q be x and P be 0, or Q is 0, but P happens to be minus y, or as a third option, if Q is 1/2 times x and P is -1/2 times y, then this expression on the left hand of the right hand side gives us 1, and then we have the area of our region D evaluated as a line integral. So the then this line integral over that along that closed curve C gives us the area of that region enclosed by the curve C. So as another example, let me ask you to compute the area enclosed by an ellipse, which is given by the equation. So area of an ellipse given by the equation x squared over a squared plus y squared over b squared equals 1. Okay, pause the video and try and use Green's theorem to find the area of such an ellipse. Alright, so I hope you paused it. This area can be found using this relation, which is a consequence of Green's theorem. Let's choose Q and P in such a way so to have this equation satisfied, we could parameterize our ellipse by taking x be a times the cosine of t and y be b times the sine of t as t changes from 0 to 2 pi. If we take this parameterization, this pair of functions will give us the points along the ellipse with axes a of length a and b, and then this area can be found as the line integral of p, which is now minus a half times y dx plus q with respect to dy with respect to y, so that's half times x dy. So this line integral is then integrating from 0 to 2 pi. Well, what is y in this case? It's b times the sine of t, so it's minus a half times b times the sine of t multiplied by dx, which in this case will be minus a times the sine of t dt. That's the first term, plus we have half times x, so x is a times the cosine of t, times dy, which is now b times cosine of t dt. dt. So this integral, the integrand, if you look at it, it's just 1/2 times a times b, because here we have sine squared of t, here we have the cosine squared of t, and the common factor is just 1/2 times a times b. So what we have here is a half times a times b times the integral from 0 to 2 pi of dt. So that's just giving us a factor of 2 pi. So if we find this area to be pi times a times b, this way we found the area of an ellipse. Okay, I hope you enjoyed this video, and I'll see you in the next one.